we start again?
Shall we start again? Okay, we can start again. Yeah. It was only a minute. Okay, good afternoon everyone. So, we are discussing removability and non-removability in bipartite matching code graphs. Right? And what we discussed last time, what we concluded with last time, was that an edge of a bipartite matching code graph, except for K2, is not removable if and only if you have a figure like this. Right? So when you remove the edge, there is a set of vertices whose neighborhood is the same cardinality as its own set, as its own cardinality. And of course this is a proper subset of the whole color class. And that means all the edges after removing AB, they go like this, inverted N shape, or it doesn't really matter, you can make it N shape. And the edge AB actually goes from top left to bottom right. Yeah, but we can actually make this stronger. I forgot to mention this point. In fact, what you can do is you can apply 2.11, which is basically the base case in proving Dulmage-Mendelsohn decomposition. You can actually make sure that either this part is matching covered or this part is matching covered. So we will actually use that strengthening for the next part. And in fact, I will state this. So we will make this part right hand side matching covered. I'll call this A1, B1, and we will call this simply A minus A1 and B minus B1. Right? The reason for that will become clear when we see the next result. Yeah, so let's write this down. This is 8.2. An edge E, or rather an edge AB of a bipartite matching covered graph GAB. And of course, in general, when I use notation like this, it should be assumed that little a belongs to capital A, little b belongs to capital B. Okay, I won't write that. An edge AB of a bipartite matching code graph not K2 is non-removable if and only if, and the second part I will just write down. So this is if and only if we have this drawing. Maybe I should just yeah, sure. If and only we have this drawing where the conditions are that the graph induced by A1 union B1 is actually matching covered, and A1 is a proper subset of A, and AB is the only edge in, consider the edges going from A minus A1 to B1. That's it. Is the statement clear? Yeah, so you have a proper subset A1 of A. The graph induced by this is matching covered. Right? A lot of things I have not written down. Right? Basically, I mean that there is a partition of capital A and of capital B with this property. Right? And those things are just there in the figure. Yeah? So this is the statement. Is the statement clear? Okay, so this is basically an immediate consequence of 2.11. So therefore, I'll just say QED. Yeah. Of proposition 2.11, which is basically Dulmage-Mendelsohn But instead of looking at the whole decomposition, you just look at this part is matching covered and the rest of it is whatever, right? And then inductively you can get bunch of matching covered pieces, but we are not doing that. We are just doing one step of Dulmage-Mendelsohn. Okay? So basically 2.11 says that any bipartite matchable graph that is not matching covered breaks into this kind of thing. You can think here you remove the edge AB, now you apply 2.11. That's what 2.11 was. And 2.11 was an exercise in your assignment 1. For at least for some of you, maybe not for all of you. Yeah? Any concerns regarding the statement? Is it clear? All good? Okay. So now what we are going to do is, one other point I want to mention is this A1 union B1. Actually, what Lucchesi-Murty do is they consider partial of A1 union B1 and they consider this as certificate for non-removability of the edge AB. Yeah, this is what they call the certificate for non-removability. Okay. But I would also like to think of just A1 union B1 itself as the certificate for non-removability. Okay, so I'm going to, instead of just using this, I will also use the same term for today for just the set A1 union B1 to make my life a bit easier. Okay, so this set itself I will call it the certificate for non-removability. Is that okay? But yeah, technically speaking, they look at the cut of that set. Okay, fine. So now what we'll do is we will consider two adjacent edges that are not removable. Okay, and we will look at the corresponding certificates for non-removability and see what they look like and if there is any relation between them. Okay, the first, and before we go there actually, let's make one more quick conclusion of 8.2. What can you say about braces of order 6 or more by using 8.2? Let me know if you figured out. What can you say about removability of edges in braces of order 6 or more? Right, if you already know, good, but use 8.2 now. Okay. So, using 8.2, can you say something about the removability of edges in so-called big braces? When I say big brace, I generally mean 6 or more vertices. Right? Also in our meeting today earlier. Okay. So that's what a big brace is. Okay, let me know if you have any ideas. right? So your brace is order 4 or less. Yeah, so the point is, here you have, if you had a non-removable edge in a brace, right, it would look like this. My brace is not K2, any other brace. It's order, you don't even need to assume anything about the order. Supposing you have a non-removable edge in a brace that is not K2, then this is the drawing. Now observe that this fellow is the shore of a tight cut. Take all the left hand side and this vertex. Well, because it is a brace, it should be trivial. That means that there is only one vertex in the complement. Well, complement will then be just this fellow, one vertex here. That means one here, one here. Now by symmetric argument, there is only one vertex here. That means the whole graph has 4 vertices. You're done. Right? So therefore, in a brace of order 6 or more, every edge is removable. Yeah? No? Did I cheat? Right? You have some nice shores of tight cuts. They have to be trivial. Right? So therefore you get only 4 vertices. In fact, even tells you what the brace looks like. It is basically a C4 where one edge has multiplicity 1. That's it. And the other possibilities, of course, K2, which we threw out in the beginning. Those are the only braces that have non-removable edges. Either it is K2 or it is C4 with one edge having multiplicity 1. Every other brace, every edge will be non-removable. Right? So I'll just write down the 6 vertex version. In a brace of order 6 or more, each edge is removable. Proved. So next thing is, let's consider non-removable edges in a bipartite matching code graph that are incident at a common vertex. We will just focus on 2 edges for now. Okay? So next, a pair of non-removable adjacent edges. So let's start with an example, right? The example cannot be a brace of order 6 or more. And order 4 and 2 is just not very interesting. I want something that is ordered at least 6. So I will take K33 minus 1 edge. Is that okay? Fine. Let's try K33 minus 1 edge. Yeah, that's K33 minus 1 edge. Let's consider this as the vertex A, this as B1, this as B2. Clearly these 2 edges are non-removable. In fact, they are degree, one of the end is a degree 2 vertex. But we will actually apply Lemma 8.2 and get the drawings and see what it looks like. Right? Let me also give labels to other vertices. So these are, let me call them A1 and A2. And let me call this fellow little b. Okay? This is my graph. Apply 8.2. See if you can make the drawings. There may be multiple ways of drawing it, but that's okay. right? So apply point 2 to the two edges A, B1 and A, B2. These are the two non-removable edges to which I want you to apply the lemma. Maybe there are multiple ways of doing it. What I would like is, I want to make this side as big as possible and this side as small as possible. Right? Because it doesn't say that there is a unique way of partitioning like this. In fact, I don't think that is true. Maybe now we'll also make it for B1. I know it's symmetric. Yeah. The labels are important. Yeah. I want to compare the two things along with the labels. Yes. For AB2, for AB1. Yeah, good. And here you go. Yeah. Okay, cool. Yeah, AB2. Yeah, now make it for AB1. Yeah, this seems fine. Just maybe if possible, flip the things A and B1, flip them so that it looks more like the drawings there. But I mean, in the grand scheme of things, it doesn't matter. A and B2, yeah, but there are more edges here. Draw all the edges, and same here. Yeah. Okay, so looks like pretty much everybody has gotten their drawings, or almost. Right, so let's apply it to A, B1, and I'm going to follow this drawing in terms of how things are drawn, right? So I'll put A here. I will put, turns out I'm able to make this 2 vertices and 4 vertices. I'll put A, B1 like this. Now, of course, because A has only 2 neighbors, B2 better be here. And now B2, B2 and B1, they both have 3 neighbors, so well, I don't have much choice. No, this is B. B2 has 3 neighbors, so all 3. Okay, and the only edge actually missing is AB, right? Because I removed one edge from K33, so I basically need to put all other edges. Okay, this is my one drawing. Alright, let me label these. These are A1 and A2. Is that correct? This is one drawing. This is for the edge AB1. Let me also label the sets A1 and B1. Those are the two sets I will label. Capital A1. This is my capital A1, and this is my capital B1. Yeah. And now let me do the same thing for the other edge. Now I should just be able to imitate it. This is AB1. This is going to be my B2. This is still going to be B. This is going to be, maybe I'll swap them, A2 and A1, just for the sake of symmetry. And now B should go to everybody except A. Okay, and this is my set A2, and this is my set B2. Yeah, this is when I apply it to AB2. These are two possible drawings I can get by applying the lemma. Right? I'm not claiming this is the only way, but this is one way. Yeah. Okay. Observe that the certificates, I'm referring to these sets A1 union B1 and A2 union B2. Observe that they are not actually disjoint in this case. In fact, A1 is equal to A2, and B1 and B2 have a common element, which is little b. Yeah, in this example. A1 is actually equal to A2, and B1 and B2, their intersection is exactly one element, which is B. Yeah? The certificates are not disjoint. Yeah? If they were disjoint, the drawing would look very nice. If I had disjoint sets, if A1 union B1 was completely disjoint with A2 union B2, well, I don't need to say completely, disjoint means disjoint. Right? If these two sets were disjoint, then the drawing would be very nice. Let's make a drawing, an abstract drawing, because it doesn't happen in this example. Then the drawing would look something like this. I have A1 and B1. I have A2 and B2. And then I have A minus A1 and A2 and B minus B1 and B2. Right? So this would be my A1. Let me make sure I'm putting things the right way. A1, B1, yeah. If they were disjoint sets, then I would get a very nice drawing. Why is it nice? Let me explain that. For the sake of example, I will put some vertices, 3 here, 3 here, 4 here, 4 here, and I don't know, this is A minus A1 minus A2, this is B minus B1 minus B2, so there will be some vertices, I don't know, 1, 2, 3, 4 again, I don't know, 1, 2, 3, 4, okay. If they were disjoint, A1 union B1 and A2 union B2, then I would get a drawing like this. Let's complete this drawing. Where is the vertex A? Vertex A, which is the vertex where we are looking at two non-removable edges incident at vertex A. Right? One of the edges is AB1 and the other edge is AB2. So where is the vertex A in this drawing? A is not in A1, A is not in A2, so therefore A is in A minus A1 minus A2. A is here. Where is B1? B1 has to be in capital B1. Right? We applied the lemma. B1 has to be in capital B1. B1 would be here. Likewise, B2 would be here. Yeah? If they were disjoint. This is all under the assumption if A1 union B1 intersection A2 union B2 is empty, then we get this drawing. Yeah? And now let's figure out what is the neighborhood of B1. What is the neighborhood of B1 in this graph? What is the neighborhood of B1 here? It is A1. And the only edge going out is this fellow. Right? In fact, we can make a stronger statement. The only edge going from B1 to A minus A1 is this edge. We would be able to conclude that the only edge going from B1 to A minus A1 is the edge AB1. The only edge going from B2 to A minus A2 is the edge AB2. Yeah? I would be able to make all these conclusions if I had this situation going on in life. Yeah? You all agree? No cheating? That's this nice drawing. What is nice? This gives you a way to visualize and simultaneously certify the non-removability of both edges. I don't need to have two drawings, one for this fellow, one for this fellow. I can make a single drawing like this, and this tells me immediately that these edges are non-removable. If I remove this edge, then any edge that has one end in A1 and the other end outside will stop being matchable. Remember, the whole graph is matching covered. Definitely there are edges from A1 that go to somewhere else outside this set. Every such edge, whether it goes like this or it goes like this, it needs to use this edge in the perfect matching. If I remove this edge from the graph, then all such edges that are going from A1 to outside B1, they all become unmatchable in G minus AB1. Right? And similarly, all edges leaving from this set and going outside this set, they will become unmatchable if I remove the edge AB2. Do you all agree? This gives you a way to simultaneously certify the non-removability of adjacent edges. Of course, non-removability refers to each edge at a time. We are not talking about the set being non-removable, right? We are talking about non-removability of each edge, right? Yeah, do you all agree? It would be very nice if we had this. Turns out we always do. If the vertex A has degree 3 or more. That is what Loas and Vanpala proved. If this vertex A has degree 3 or more, you get this very nice drawing. Yeah? This is the next result that we are going to prove. If the degree of A is 3 or more, then these certificates of non-removability, I am referring to the sets A1 union B1 or A2 union B2, they are actually going to be disjoint. What you are seeing here in this example, this is happening because the degree of little a is 2. Otherwise it wouldn't happen. Okay, that's what we'll prove now. Go ahead. There could be. I did not make any statement about that. The only edge going from B1 to A minus A1 is this edge. From A1 I have no idea what are the edges. Gauss Sampala doesn't say anything about it. Sorry?
For B2?
Because of B2. Good point. Thank you. Yeah, Santosh is right. Yeah, there are no edges like this. There are no edges like this because the only edge going from B2 to A minus A2 is this fellow. Yes, you're right. There are no such edges. Thank you. Yeah, good. Yeah, from A2 we can have edges to not to B1 again. Yeah, now the same point. From A2 the edges can only go to this set.
So
Yeah, good point.
neighborhood of A1 is equal to B1 and maybe some vertices from B minus B1.
Yes, that's right. Yeah, that's a good point. Yeah. That's right. Yeah. Okay. Alright, so this is what we'll prove, right? We'll prove that when the degree of A is 3 or more, then these certificates, the sets A1 union B1 and NT union B2 are going to be disjoint. Okay? I'll erase these drawings. We will anyways probably make them later again. So I will not write down statement and proof. I'll just write down some assumptions. GAB is a bipartite matching covered graph. AB1 and AB2 are non-removable edges. The degree of A is at least 3. Apply Lemma 8.2 to AB1 and AB2. I'll make a drawing. I'll make 2 drawings maybe. I don't know about the cardinalities. All I know is that this is equal to this is equal to this in cardinality. I know the vertex little a is here. The vertex little b1 is here. This is my capital B1. This is my capital A1. Therefore, this is A minus A1. And this is B minus B1. This is our edge AB1. All the edges on the graph, apart from this edge, they look like this. This is apply Lemma 8.2 to AB1. And well, AB2 is going to be on the left side. That's unfortunate. Anyways, fine. Okay, this is my A2, B2, this is my A minus A2, this is my B minus B2, this is my edge AB2, and all other edges of the graph in this drawing, they go like this. These are two drawings of the same graph. Yeah? Okay, so we have applied the lemma and we have gotten these drawings with the notation. Then, the conclusion we want to prove is that B1 and B2 are actually disjoint and A1 and A2 are also disjoint. I have a question for you. Which one of these implies the other? Does B1 intersection B2 disjoint imply A1 intersection A2 disjoint, or is it the other way around? So these are the two statements. Implies immediately, basically, without much thinking. Yeah, so just to repeat, we don't have the drawing I made earlier, right? The drawing I made earlier, where I had 6 boxes, we don't have that, right? We want to actually prove that that drawing is a valid drawing. What we have is these 2 different drawings of the same graph G. This is also G, this is also G. And in fact, we don't know what is the relation between these 2 drawings. At some fundamental level, we are really clueless. Right? Which one is yours? So one more point I want to mention is I'm not asking you to prove either of these 2 statements right now. Eventually I will. But right now I'm not asking you to prove either of these statements. Right? And if you have a proof for either of these statements, your proof must use the hypothesis that degree of A is 3 or more. Did I say 3 or more? Yeah, 3 or more. Because if you don't use that hypothesis, then here is a counterexample to both statements. Neither is A1 intersection A2 empty, nor is B1 intersection B2 empty. So if you have a proof of either of them, you must use the hypothesis that degree of A is at least 3. Any proof that doesn't use that hypothesis is false. Sorry?
You do not disprove the existence of such A1, A2, B1, B2 in that example.
No, but this is, we haven't applied Lemma 8.2. I mean, basically what I'm saying is, if you apply Lemma 8.2 as it is, you should not be able to prove these statements without the hypothesis that degree is at least 3.
It does not work for any...
Yeah, here is an example where it will fail. Right? So, any proof of these statements must use the hypothesis that degree of A is at least 3. And for degree of A is at least 3, we will prove it. So, that's the whole point. But yeah, the question I asked is, which of these 2 statements would imply the other one? Right? Did I say empty or did I want to say non-empty? Okay, let's see. Yeah, go ahead. Is this drawing implying that these are disjoint? Okay. I'm trying to think whether I wanted to say something else. Give me a second. So here's what we will do. I'm also confused what I want to do. Okay, let's see. We will prove that B1 intersection B2 is actually empty. This is what we will prove. Does this imply that A1 intersection A2 is empty? Yeah, I'm also a bit confused right now. I mean, I know how to prove the thing I want to prove, but I'm not sure if the story I have is the right story. That is something I'm still figuring out. Yeah, go ahead. Other way around is true, right? Is that right? If A1 intersection A2 is empty, yeah, so this seems to be correct. If A1 intersection A2 is empty, then B1 intersection B2 is empty. Is the same thing what Anjali said? Is that what you also mentioned? Okay. If A1 intersection A2 is empty, then B1 intersection B2 is empty. Because let's look at the contrapositive. If this is non-empty, B1 intersection B2, so there is an element that is common to both of them. That can't be little b1 or little b2. Observe that little b1 is actually not in all the other neighbors of this fellow are in this set. Little b1 is actually here. Little b2 is actually here. So the common element between b1 and b2 cannot be little b1 or little b2. It has to be some other b, little b. And all neighbors of little b are actually here, but all neighbors of little b are also here. Therefore, I will get common intersection, I will get non-empty intersection between A1 and A2. So what did we prove? If this is not true, then this is not true. Therefore, this implies this. Yeah, okay, fine. That's what we proved. Fine. I don't know if I'm going to use that actually. Okay. Anyways, fine. What we will prove is that both of these statements are true. Okay. We will prove that B1 intersection B2 is empty and A1 intersection A2 is empty. Okay, this is what we'll prove. Alright? Sorry? Typo? Oh, sorry. Intersection. Thank you. We'll prove that both of these intersections are empty. Yeah? Okay. Questions, concerns? Okay, if not, let us continue. Let's see if we can finish this and then we'll probably take a break. So we must use the fact that the degree of A is at least 3. Yeah? Otherwise, this statement is false. Both statements are false actually. Yeah? So how shall we use the fact that degree of A is at least 3? I'll give you a hint. This course is based on a book called Perfect Matchings. Yeah, so what I'm saying is we have to use the fact. In order to prove these statements, we must use the fact that the degree of the vertex A is at least 3. How will we use that? And my hint is that the book we are following is called Perfect Matchings. can we get a perfect matching that behaves nicely with both of these drawings? I don't know what behaves nicely means. Well, I do know what it means, but I don't want to tell you. Can we get a perfect matching in this graph that behaves nicely with this drawing and also with this drawing? And what does behave nicely mean? Okay, while you're thinking, I'll make some space because I'm likely to need more space. So the question is, let's make one more drawing. This is the vertex A, this is B1, this is B2, but this has at least one more neighbor. In fact, because both of these are non-removable, it also means that their multiplicity is 1. Therefore, degree being 3 also means that there is a third neighbor. Right? There could be many more neighbors, I don't know. But there is at least one more neighbor that is neither B1 nor B2. Okay, so looks like everybody has figured it out. Take a perfect matching that contains neither AB1 nor AB2, right? And that means it will match A to some other vertex, right? Because AB1 and AB2 are actually multiplicity 1 edges, right? So we are not using this edge. Well, if you don't use this edge, then you can't use any of these edges. Therefore, that perfect matching will have empty intersection with this cut. Its restriction will be a perfect matching here, its restriction will be a perfect matching here. And likewise here, for the same reasons. That's exactly what we'll do. M is a perfect matching of G containing neither AB1 nor AB2. This cannot happen when the degree is not 3. This is where you will use the hypothesis. Okay? Observe. M's intersection with partial of AI union BI is empty for each I. You agree? Okay? It behaves nicely. This is what I mean by behaves nicely. Maybe this is why they called nice subgraph for conformal subgraph. I don't like the word, but anyways, behaves nicely. Okay? Good. This is going to be our friend M. Maybe let's use some nice color for M. Pink. M is the pink perfect matching. Okay? Alright. Now we want to prove these facts, right? Okay, let's do some very, very basic stuff. Cardinality of B1 plus cardinality of B2 is equal to cardinality of B1 union B2 plus cardinality of B1 intersection B2. Yeah? Everybody agrees with this? Yeah? Okay. Right.
That's
Minus. Is it? I moved it. Right? De Morgan. Right? Cardinality of this fellow is plus cardinality of this fellow is simply the cardinality of union, but I have to add the intersection again because it was counted twice on the left hand side. So I have to count it once more. Right? Okay, this is fine. Good. Alright, so nothing deep has been said so far. But now let's try to make some progress using this perfect matching M. Where are all the vertices in B1 matched by M? All the vertices of B1 under the perfect matching M are matched into A1. All the vertices of B2 are matched into A2. Therefore, I can make the statement that all the vertices of B1 union B2 are matched with vertices in A1 union A2. Yeah? Okay, this is basically just following from here. Each vertex in B1 union B2 is matched by M with some vertex in A1 union A2. Yeah? What does this tell you about the cardinality of the two sets? Equal? Or something weaker? Each vertex in B1 union B2 is matched with some vertex in A1 union A2. A1 union A2 has at least as many vertices as B1 union B2. Right? We can't say equality. We did not say the other way around. Right? This implies that B1 union B2, its cardinality is less than equal to the cardinality of A1 union A2. Sorry. Oh, one. Sorry. Yeah. Thank you. Yeah. Yeah, you all agree? This is fine? Okay. Now let's think about, this is good, right? We can replace this fellow by A1 union A2, but then we have to convert the equality to less than equal to. Yeah? Okay? To make progress, we also need to do something about this fellow. Basically, the plan is to convert everything into terms of A's. Right now, everything is in terms of B's. We will convert everything into terms of A's, and then we will try to do something from there. Right? So to do that, we have done something for this term. We should also do something for this term. Can we make a similar statement here? Can I say that is the following true? Can I also make a similar statement about this and this? Is this true? Think about it. Supposing it is true, then what does it mean? Let's try to see what would, supposing we prove this. Then I can say that this is less than equal to A1 union A2 plus, because I am assuming this is true, I can, but what is this? This is simply cardinality of A1 plus cardinality of A2. Hey, but what does that mean? What does that mean? Yes, this is anyways equal to this. Therefore, everything holds with equality. These two are anyways equal. So if we are able to prove this, then everything here holds with equality. In particular, this is equal to this, and this is equal to this. Yeah, that would be nice. But anyways, let's, when we have to do something about that, we haven't still proved anything of interest to us. This is where we want to go. But maybe let's just try to think about this for now, right? Can you all think about this? Is it true that B1 intersection B2 is less than equal to A1 intersection A2? And I want you to pay attention to this argument. How did we prove this? Think about that. Same argument works? Yeah, okay. Maybe write it down. Yeah, okay. Also, if you have figured this out, great. I want you to also think about this. How do you prove that some set of vertices in a bipartite matching covered graph is the empty set? Some set of black colored vertices or white colored, same color, right? If you want to prove that some set, some monochromatic set, if I may call it, because all of them are the same color, right? If I want to prove that some monochromatic set is actually the empty set, how would you prove such a statement? Is there any characterization of bipartite matching chord graphs that would help you to prove such a statement? Think about all the characterizations of bipartite matching chord graphs that you know. Maybe write them down. If you want to show that some monochromatic set is empty, maybe there is something you should prove, then it would imply it is empty. Okay, so there are two things. One is, how would you prove such a statement using characterizations of bipartite matching chord graphs? This will become relevant soon. And is this true? And if this is true, write down a full argument. And I'll make some more space. But that's not going to be easy. My suggestion is, think about one vertex at a time, right? Don't try to think about, if the whole set is confusing you, just take one vertex at a time. Take one element of B1 intersection B2. Of course, B1 intersection B2 could be empty, in which case any conclusion you make is probably correct anyways, right? So think of one element in B1 intersection B2. Now think about the perfect matching M. Where does it match it? And see if you can make progress from there. And I also want you to, so if you have figured this out, I would also like you to introduce now the neighbors of B1 intersection B2 into the picture. Where do they lie? where are these fellows? Of course, this would be empty set, in which case it doesn't matter. Right? So think of B1 intersection B2 as non-empty for the sake of example, for the sake of making progress. Right? Where would this neighborhood lie? Can you say something about the neighborhood? For the sake of example, you can put one vertex here, little b. Supposing this little b is here, and the same little b is also here. Where are the neighbors of little b? Right? When you are stuck, just put a vertex. Thinking about things abstractly is not the best idea always, right? Just put some vertex and think of one vertex. Also, let's put some more information in the drawing. Right? We know that B1, we know that little b1 is not here because all neighbors of A except little b2, they belong to this set. So therefore little b1 is in this set. And likewise little b2 is in this set. So this little b fellow is neither little b1 nor little b2 because it is in both sets b1 and b2. Right? That's also information. Right? So you know that any element in the intersection of b1 and b2, if it exists, it is neither b1 nor b2. It is something else. Right? All of this is kind of helpful to make some progress. Yeah, so let's make a few observations. Observe that this little b fellow, all its neighbors are actually in A2, right? Because little b is not equal to b2, and this is the only edge going like this. So all neighbors of little b are in A2. Likewise, all neighbors of little b are in A1. Therefore, the neighbors of all vertices in B1 intersection B2 are contained in A1 intersection A2. You all agree? Neighbors of all vertices in B1 intersection B2 are contained in A1 intersection A2. Yeah? And we wanted to prove this. Well, we know that this is true. The neighborhood of B1 intersection B2 is less than equal to A1 intersection A2. You agree? Because it's a subset. Yeah, this is true. Yeah. What can we say about the neighbor B1 intersection B2 and its neighborhood? Do we know anything about them? Do we know anything about the cardinality of a set and its neighborhood when the set itself is monochromatic? Right? We know Hall's theorem kind of thing. Right? Well, at least one for some condition. I'm not going to put that right now. I'm just going to put the easier statement. We know that the cardinality of B1 intersection B2, we know that its neighborhood has to be at least as large as itself. This much we know. This we know for all bipartite matchable graphs for every single set, every single monochromatic set. Right? And this is less than equal to, right? In particular, we have proved this. Yeah, and we also kind of went through this in order to arrive at this conclusion. Yeah. Okay, so therefore all I wrote here is correct, right? So let's just recall what we did. We wrote down this very innocent equation, and we observed using this perfect matching. Right, we use the perfect matching very crucially to conclude that the union of B1 and B2 is less than equal to the union of A1 and A2. Right, so that we already had, and now we also wrote a similar statement for the intersections. For that we made some observations. Right? Yeah. Okay, so we have this. But hey, cardinality of A1 is equal to cardinality of B1, cardinality of A2 is equal to cardinality of B2, therefore everything holds with equality. Do you all agree? Everything has to hold with equality. Since cardinality of AI is equal to cardinality of BI for each I, everything holds with equality. Yeah? You all agree? This is actually equal to this. This fellow actually has to be equal to this fellow because this was term-wise inequality. Right? You remember all that? This was also term-wise inequality. So this also has to be equal to this fellow. Do you all agree? But what does this mean? These two being equal. What does that mean? Right? That means that all of this is also going to be equality. Right? I can put equality everywhere. All of this is equality. This is not subset of. This is equal to. Is that correct? Yeah? In particular, the set B1 intersection B2, it is equal to its cardinality is equal to its neighborhood's cardinality. What does that mean? In a bipartite matching chord graph, if you find a set of black vertices whose neighborhood has the same cardinality as itself, what does that mean? That set has to be either empty or full. Yeah? For any non-empty proper subset, the neighborhood should be at least one more. So therefore, for this to hold with equality, this is the main point now. This. For this to hold with equality, it means that B1 intersection B2 is either the entire set B or it is the empty set. Can it be the entire set? It can't be the entire set, right? Because even B1 is not the entire set. So how can B1 intersection B2 be the entire set? Therefore, B1 intersection B2 is in fact empty, right? B1 intersection B2 is empty, right? This implies that B1 intersection B2 is empty. Yeah? No common element between these two sets, right? But we also know that the cardinality of B1 intersection B2 is equal to the cardinality of B1 intersection A2. Okay. This is the point where we conclude. Okay, so my first question, does one imply the other? I take it back. Yeah, now that I think about it, it was not a great question. Yeah, so in fact, this is the point. Because we know that everything is holding with equality, now that we know this is empty, it follows that this fellow is also empty. Right? In fact, this, yeah. So therefore, this fellow is also empty. This is what we wanted to prove. Yeah? Okay? Fine? Alright, good. You may say, oh, two edges. What's the point? Two non-removable edges adjacent. We did so much work to prove this. Observe that you can have 10 edges, all having a common vertex, and you get a similar drawing now. Apply the same thing to two vertices at a time. That is the Lowas-Sampala result. So I'll write down the result. There is a reason I did not write down the result. Right? The result actually takes multiple non-removable edges, all incident at a common vertex, and then basically proves this for two edges. Right? So now we'll write down the general statement, and the general statement follows from what we have proved. Yeah. Maybe you can take a short break here. In the meantime, you all can try to write down the general statement yourself in the next 10 minutes. Right? There is no class here, right, after us? Yeah. So we might go up to 4:15 or 4:30. Yeah. So the DIY for the next 10 minutes is generalized to the following situation where you have a single vertex A and all these are non-removable edges, AB1, AB2 up to ABR, all of these are non-removable, and the degree of the vertex is D. This is BD, and D is at least 3. And of course R could be equal to D. It is possible that all edges incident to the vertex are non-removable. Okay, so that's your exercise. Okay, thank you. We can stop recording and we'll start again in 10 minutes.